In this section on basic aerodynamics, we'll briefly discuss the four forces, aerodynamics of a wing, center of gravity, and three-axis movement. The four forces include lift, weight, thrust, and drag. Lift acts upwards. Weight acts downwards, opposing lift. Thrust pulls forward, and drag acts in a rearward direction, opposing thrust. When the aircraft is in straight and level flight at a constant airspeed, lift equals weight and thrust equals drag. Let's look at each force separately. Lift is an upward force created by the movement of an airfoil through the air. An airfoil is more commonly called a wing. Bernoulli's principle says that as the velocity of a fluid increases, its pressure decreases. Well, air is a fluid, and the curvature of the airfoil forces the air above it to flow more quickly than the air below it. The lower pressure above and the higher pressure below cause the airfoil to rise. The remainder of lift is created when air strikes the bottom of the airfoil and is deflected downwards. This creates an equal and opposite reaction that pushes the airfoil upwards. Remember, the rotor blade on a helicopter is a rotating airfoil, and it generates lift just like an airplane wing. Weight is the force exerted by the Earth's gravity. It acts vertically toward the center of the Earth and opposes lift. Thrust moves the aircraft forward through the air. In an airplane, the propeller supplies thrust. In a helicopter, the main rotor provides thrust. In fact, helicopters are unique in this respect. They can direct their thrust forward, aft, or sideways by tilting the main rotor. In practical terms, there really is no distinction between lift and thrust in a helicopter. The main rotor blades produce both. Thrust is simply that part of vertical lift that's been redirected into horizontal lift. Drag is the force that retards the movement of an aircraft through the air and opposes thrust. There are two types of drag. Parasite drag is the portion of total drag caused by form resistance and skin friction. Parasite drag increases as airspeed increases. Induced drag is the part of total drag that results from developing lift. As airspeed increases, induced drag decreases. We can see the relationship between drag and speed in this graph called the drag-speed chart. You can see that as airspeed increases, parasite drag increases, and induced drag decreases. Where these drag coefficients cross at point B, total drag is lowest. If we were to drop down here to our speed axis, we would find the maximum glide range airspeed. And this is called best glide speed. This is the speed at which the helicopter will travel the maximum horizontal distance per foot of altitude lost. Let's look at the parts of a wing now. As the wing moves through the air, the oncoming air will split around the wing over the top and through the bottom around the leading edge. The airflow on top and on bottom meet again at the trailing edge. The chord line is an imaginary line that runs from the leading edge to the trailing edge. Relative wind is the direction of airflow with respect to the wing. It's created by the motion of an airfoil through the air, by the motion of air past an airfoil, or by a combination of the two. For a helicopter, the relative wind is the flow of air with respect to the rotor blades. The relative wind is parallel to the flight path, but moves in the opposite direction. Relative wind may be affected by several factors, including the rotation of the rotor blades, horizontal movement of the helicopter itself, or the flapping of the rotor blades. Also, wind speed and direction. The angle between the chord line and the relative wind is the angle of attack. Don't confuse angle of attack with pitch angle of the rotor blades. Pitch angle is the angle of the blades relative to the helicopter itself. The angle of attack is the angle of the blades relative to the oncoming wind. As the angle of attack increases, lift increases. As the angle of attack decreases, lift decreases. So in a nutshell, increasing pitch angle increases angle of attack, which in turn increases lift. Decreasing pitch angle does the opposite. Remember, As lift increases, induced drag increases and will tend to slow down the rotor blades. Additional power will be required to prevent this decay in RPM. Critical angle of attack is reached when the angle of attack is so great that the air can no longer flow smoothly across the top of the airfoil. The airflow becomes turbulent and drag increases. There's a sudden increase in pressure on top of the wing and lift is lost. We say that the wing or rotor blade has stalled. There are two ways that you can increase lift. Increase the speed of the aircraft through the air or increase the angle of attack. Now in a helicopter, we have to keep the rotor RPM at a relatively constant speed. Therefore, our only choice is to vary the angle of attack. We'll finish up basic aerodynamics by reviewing center of gravity and three axes of movement. The entire helicopter is balanced around an invisible point called the center of gravity and is the center of the helicopter's total weight. This point, abbreviated CG, is usually located near the rotor mast. The helicopter has three axes of movement which intersect at the center of gravity. Imagine running a shish kebab skewer from the nose to the tail. This is the longitudinal axis. Moving the main rotor side to side is moving it along the longitudinal axis. Put the skewer through from one door to the other and move the main rotor front and back, and you control the attitude of the helicopter about the lateral axis. This motion is called pitch. The vertical axis goes from the top to the bottom through the center of the helicopter, where the rotor mast is. Movement about this axis is controlled by the anti-torque rotor and is called yaw. We often refer to control of this direction as heading. Enough said about basic aerodynamics. Let's look at the checklist now for the next section on helicopter systems and flight controls. Then we'll go on out to the ramp and examine these systems up close. We're going to look at main rotor systems, rotor clutch, the freewheeling unit, carburetor icing, the anti-torque rotor system, flight controls, including the collective, throttle, cyclic, anti-torque rotor pedals, and abnormal vibrations. Let's go outside and take a look at these systems close up. Let's get right to the heart of the matter and look at what makes a helicopter so special. Its ability to hover and take off and land almost anywhere. And the feature most responsible for that is the main rotor system. There are three basic types of rotor systems. Let's take a closer look at a couple of them. The fully articulated rotor system consists of three or more blades. Each of these blades is attached to the main rotor hub by a variety of hinges. A horizontal hinge called the flapping hinge allows the blade to move up and down. A vertical hinge called the drag hinge allows the blades to move back and forth. Each blade can also twist or feather in order to change blade pitch angle. So the main rotor blades in a fully articulated system can flap, drag, and feather independently. A semi-rigid rotor system has two blades. Both blades are rigidly connected to the main rotor hub, which is free to rock and tilt about the rotor mast by way of the teetering hinge. As one blade tilts up, the other blade tilts down an equal amount. Therefore, we say the main rotor blades of a semi-rigid system flap and feather as a unit. Semi-rigid systems don't have a drag hinge. We'll see why a little later. Most helicopters use either a fully articulated or a semi-rigid main rotor system. A less common third type is a rigid or hingeless system. Flapping, dragging, and feathering is absorbed by blade bending and flexing in a rigid system. Later, in helicopter aerodynamics, we'll talk about why the rotor blades must be able to drag, flap, and feather. But first, let's talk about some other important helicopter systems. Closely related to the main rotor system is the clutch and the freewheeling unit. Most helicopters, except the very lightest ones, use a clutch to engage the main rotor system. Trying to start a helicopter engine with the rotor engaged It's like trying to start your car while it's in gear. Pretty difficult, if not impossible. Unlike an airplane propeller, which is relatively light, the main rotor system of a helicopter is too heavy for the engine to start if they're directly connected. Some helicopters use a manual clutch, and others, like the Schweitzer 300C, use an electric motor. The clutch allows an engine start without having to overcome the extra drag created by an attached rotor system. Here you can see an electrically actuated clutch gradually tightening the belts that will bring the load of the rotor system online and up to speed without stalling the engine. The freewheeling unit is a critical system. Without it, autorotation wouldn't be possible. The freewheeling unit disconnects the main rotor system from the engine in the event of an engine failure. Otherwise, the drag of the dead engine would cause an almost immediate and catastrophic loss of rotor RPM. No rotor RPM, no staying up in the air. Many helicopters use the same type of engine found in common light airplanes. And just like airplanes, some are carbureted, some are fuel injected. You already know that carburetors can sometimes ice up. But what you may not know is that a reciprocating or piston engine in a helicopter is more likely to ice up than is the same type of engine found in an airplane. This is because the freewheeling unit in the helicopter doesn't allow the windmilling effect of the rotor blades to be exerted on the engine, so the helicopter can't take advantage of the so-called flywheel effect. Icing is most likely to occur when the outside temperature is between 20 to 70 degrees Fahrenheit, with visible moisture or high humidity present. And when the throttle is partly or fully closed, ice is especially likely to accumulate. So what should you do? Use the carb heat. When operating the helicopter in conditions that are favorable to carburetor icing, adjust the carb heat to keep the carburetor air temperature gauge in the green or normal range at all times, except for takeoffs. During takeoff, the carb heat should not be used. You'll want to keep as much power available as possible during this critical phase of flight. Over here, we have the other rotor system, the anti-torque rotor system. The tail rotor, as it's also called, is located on the end of the tail boom. Its primary purpose is to counteract the torque effect of the engine. As the main rotor blades turn in one direction, typically counterclockwise in most American helicopters, the fuselage has a tendency to want to turn in the opposite direction, or to the right. If not for the tail rotor counteracting the torque effect, we'd find ourselves spinning wildly around and around. This would make directional and heading control difficult, to say the least. Foot pedals are used to vary the thrust of the tail rotor. Pushing left pedal increases the thrust of the tail rotor to the right, turning the helicopter left, and vice versa. By varying the thrust of the tail rotor, we can change heading during hovering operations, maintain heading in crosswind departures and approaches, and, in an auto rotation, maintain heading by correcting for the loss of torque. In cruise flight, the anti-torque pedals are generally used only to adjust trim, since the streamlining effect of the relative wind does a good job of maintaining the heading for us. One other thing. A moment ago I said that the primary purpose of the tail rotor was to counteract the torque effect of the engine. That is, to prevent the fuselage from spinning wildly around to the right. So, we need more positive pitch available than negative pitch in order to provide thrust to the right. But there's a situation when we need some negative tail rotor pitch. When power is removed from the main rotor, as in the event of an engine failure, the drag of the transmission will cause the fuselage to yaw in the same direction as the main rotor, that is, to the left. So in this situation, the tail rotor must also be able to provide thrust to the left to counteract the drag of the transmission during auto rotation. Now let's go into the cockpit to take a look at the flight controls.
The collective is located on the pilot's left side. The collective controls altitude. Adjusting it makes equal changes in the pitch of all the main rotor blades at the same time, or collectively. Raising the collective increases the pitch angle, which increases angle of attack, which of course increases lift. And since all blades are increased in equal amount, lift is increased equally across the entire rotor disc. Lift is decreased when the collective is lowered. The throttle is located on the collective and controls RPM. As collective pitch is increased, a mechanical linkage called the correlator, or in some helicopters an electronic governor, increases the throttle automatically to provide additional engine power. Similarly, as the collective is decreased, the throttle is decreased. In this sense, the collective control maintains desired engine power. The cyclic determines the helicopter's direction of travel. The cyclic pitch control, located between the pilot's legs, changes the pitch angle of each of the rotor blades one at a time as they pass through the same point in the plane of rotor rotation. Increasing the pitch angle of the blades at one point in the plane of rotation relative to other points tilts the rotor disc. For example, if I want to fly forward, I need to tilt the rotor disc forward, and I do this by pushing the cyclic. Likewise, if I want to move aft, I need to tilt the rotor disc aft, and I do that by pulling back on the cyclic. Similarly, moving to the sides requires that I move the cyclic to the sides, which of course tilts the rotor disc in the appropriate direction. By tilting the rotor disc, we're redirecting some of the vertical lift into a horizontal component of lift. And the more we tilt the rotor disc, the more lift we're redirecting horizontally. By controlling how much lift is redirected in this fashion, the cyclic also controls airspeed. Let's look at this in more detail. Here we see a helicopter at a stationary hover. All the lift is directed vertically. But if you want to move forward, you have to redirect some of this vertical lift into horizontal lift. By doing that, though, you've robbed Peter to pay Paul. Now there isn't enough vertical lift to maintain altitude, and you'll start descending. In order to maintain altitude, it makes sense that the vertical component of lift must equal the aircraft's weight, so you'll need to raise the collective to increase vertical lift. And remember, turning or banking increases the load factor or weight of the helicopter, requiring even more collective increase. We've covered the collective, the throttle, and the cyclic. That just leaves the anti-torque rotor pedals. As you recall, they control heading by regulating the amount of thrust that the tail rotor produces. Pushing left pedal increases tail rotor thrust. Pushing right pedal decreases tail rotor thrust. The pedals coordinate tail rotor thrust with changes in main rotor torque, enabling you to maintain the desired heading. It's important to keep in mind that the engine is providing power to both the main rotor and the tail rotor by way of the transmission. The greatest amount of engine power will be required when making a left pedal turn. Think about it. Pushing left pedal increases the thrust of the tail rotor, thus requiring more power from the engine. The main rotor RPM will decrease and the aircraft will settle if throttle isn't added. The opposite happens when pushing right pedal. Tail rotor thrust is reduced, so more of the engine power goes to the main rotor. The main rotor RPM will increase and the aircraft will rise, unless we reduce the throttle. Now that we've described the functions of the different flight controls, let's talk about how you might use them all together in an actual flight situation. Suppose you were performing a normal approach from altitude to a hover. The collective, because it controls altitude, will control the angle of descent. If you lose altitude quickly, the angle of descent will be steep. If you lose altitude slowly, the angle of descent will be shallow. Since the cyclic controls airspeed, it'll control the rate of closure, or how quickly you approach to a hover. Finally, the anti-torque pedals maintain heading and keep your nose pointed in the right direction. By skillfully coordinating all the controls, the transition from flight at altitude through the approach and into a hover can be managed smoothly. Someday you may be flying along and notice that the helicopter just doesn't feel or sound right.
Knowing what these abnormal vibrations and sounds could mean could give you a good clue as to what's wrong with your rotorcraft. Low-frequency vibrations are countable. That is, they're in the 100 to 400 cycles per second range and always indicate a problem with the main rotor system. Medium-frequency vibrations or sounds are usually associated with problems in the tail rotor system. And high-frequency sounds or vibrations typically mean there's a problem with the engine or the transmission. Think of it this way. The faster the component turns, the higher the frequency. The main rotor turns relatively slowly, about 500 RPM. Next comes the tail rotor, which typically turns about 6 to 9 times faster than the main rotor. And fastest of all are the engine and transmission, which can run upwards of 3,000 RPM. No matter what the cause may be, prudence dictates that you get on the ground as soon as possible. Well, that concludes our discussion of helicopter systems and flight controls. Let's go back to the pilot lounge now and talk about helicopter aerodynamics. In this section, we're going to focus on aerodynamics unique to rotorcraft. This includes gyroscopic precession, coning, translating tendency, ground effect, translational lift, transverse flow, vortex circulation, dissymmetry of lift, flapping, retreating blade stall, Coriolis effect and lead lag, and feathering. The spinning main rotor of a helicopter behaves like a gyroscope. Both are affected by a property called precession, a characteristic of all rotating bodies. Take a look at this simple example. If you touch a spinning object, it will tilt. But the rotating object must make another quarter turn from where you touched it before it tilts. Think of it as a delayed reaction. Well, the helicopter's main rotor is a rotating body, just like a gyroscope. When you make a cyclic control input, which is a blade pitch change, you're applying a force to a specific point on that rotating body. The rotor disc will react by tilting, but only after making another quarter turn in the direction of rotation. So precession requires that the cyclic control be designed to make a pitch change early, specifically a quarter turn before the desired effect needs to take place. The pitch angle of the blade is at a maximum at the 3 o'clock position, which is on the pilot's right. Remember, the main rotor blades turn counterclockwise. What is the effect of increasing pitch angle? It means you'll be increasing lift. If the pitch angle is at a maximum on the advancing right side, the delayed reaction of increased lift won't occur until a quarter turn later. The maximum rise in the rotor disc will be at the 12 o'clock position, in front. Similarly, the maximum decrease in pitch angle will start at the 9 o'clock position, on the left side, but the maximum decrease in lift won't happen until when? A quarter turn later, at the aft position. Consequently, the maximum lift is in front and the minimum lift is at the rear. This makes the rotor disc tilt aft. Now on to coning. Coning refers to the upward flexing of the main rotor blades when a load is applied to the system. Before takeoff, centrifugal force is the major force acting on the rotating rotor blades. This force acts outwards from the rotor mast, keeping the blades straight and rigid. At this point, the weight of the helicopter is still on the ground, not on the rotor blades. But as the collective pitch is raised, increasing the angle of attack, lift is increased. On takeoff, the weight of the helicopter is transferred from the ground to the rotor blades, and the aircraft is literally hanging from the blades. The combined forces of lift acting upwards and centrifugal force acting outwards cause an upward flexing of the rotor blades as they struggle to overcome the stress of lifting the aircraft higher. Semi-rigid rotor systems assume a conical shape due to blade bending. The blades in a fully articulated rotor system angle upwards about the flapping hinges. Coning is a factor that limits maximum gross weight of the helicopter. The higher the gross weight, the more pronounced the coning effect. The more coning that occurs, the smaller the lifting area of the rotor disc. This is one way that high gross weight reduces performance. So now we're off the ground. While hovering, you need to be alert to the horizontal thrust of the tail rotor as it tends to push the helicopter sideways. This is called translating tendency or drift, and in most helicopters, this tendency is towards the right. To counteract this drift, helicopter engineers rig the rotor mast or cyclic pitch system slightly to the left. This creates a small horizontal component of lift to help overcome this tendency. Despite this, the pilot will usually need to apply some small amount of additional lift cyclic pressure to maintain constant directional control. Once the helicopter gains forward momentum, let's say faster than that of a hover, translating tendency is generally no longer noticeable. While we're still close to the ground, we should talk about ground effect. The helicopter is operating in ground effect whenever it's within one rotor diameter of the surface. The rotor downwash can't disperse readily because of surface friction, making the air beneath the helicopter compressed. The increased air pressure resists and reduces the downwards flow of air, increasing the angle of attack, which, as you know, increases lift. Since lift is greater, we don't need as much collective and can lower the blade pitch angle a little. The reduction in induced drag improves the efficiency of the rotor system. That's why it requires less power for a helicopter to hover in ground effect, often abbreviated HIGE, than it does when out of ground effect, often called HOGE. Different surfaces influence the intensity of ground effect. Flying over a flat, hard surface works best. Other surfaces, such as tall grass, water, slopes, dissipate the static air pressure and aren't as effective, requiring more power. Now you're ready to transition from a hover into forward flight. In this phase, you'll encounter several aerodynamic events that'll affect the aircraft's flight characteristics. The first of these is translational lift. In a calm wind hover, the main rotor system draws in air from directly above. But as the helicopter begins to move forward, the rotor system can now also draw in air from in front of the aircraft. Consequently, the rotor system now has a greater mass of air, moving at a greater velocity, to work with. This increases efficiency and performance. Translational lift results from gaining airspeed, not ground speed. Although not noticeable at low air speeds, it's present any time there's movement of air across the rotor system. So even if you're in a stationary hover, you're in translational lift if the wind is blowing. When accelerating to approximately 15 miles per hour, a rapid increase in excess power develops and can be felt as a transient vibration. If the collective pitch is maintained, this excess power will make the helicopter pitch up and begin to climb abruptly. Apply additional forward cyclic to prevent the nose from rising. The additional performance available at this speed makes the translational lift effective, hence the term effective translational lift. Heading into the wind takes advantage of this benefit. The reverse phenomenon will occur when transitioning from forward flight into a hover, as when approaching to land, for example. Effective translational lift will be lost when you slow below 15 miles per hour, and the aircraft will settle if you don't increase the collective pitch. However, ground effect will tend to provide a beneficial cushion as the helicopter approaches the ground. Many new helicopter students have trouble judging when effective translational lift is going to occur. Here's a tip for you. You can anticipate effective translational lift when in low-speed flight over a movable surface, such as grass or water. The rotor downwash disturbs the grass or creates ripples in the water in a relatively evenly distributed pattern around the helicopter. As the aircraft moves forward, the circular pattern of disturbed grass or water begins to move aft. When the forward edge of this pattern comes abeam the approximate position of the rotor mast, translational lift will become effective and you'll feel the transient vibration and pitch up. Transverse flow. Transverse flow develops when there's movement of air across the rotor system. Like effective translational lift, it's only noticeable at low air speeds. In forward flight, the air passing through the rear portion of the rotor disc has a greater downwash velocity than air passing through the forward portion. This is because the air passing through the rear has been accelerated for a longer period of time and over a greater distance than the air passing through the front. The increased downwash velocity and greater downwards angle of the air at the rear of the disc decreases the angle of attack and hence the blade lift at the rear. Similarly, lift is increased at the front. Now, gyroscopic precession delays the effect of reduced lift until the blade makes another quarter turn counterclockwise towards the right side. Having lower lift on the right and higher lift on the left will cause the disc to tilt to the right. You'll usually need to apply some left cyclic in order to compensate for this tilt when in forward flight at low air speeds. Here's an almost sure bet to win you some points in a trivia contest. Ask most airplane pilots about wake turbulence, and they'll tell you about two counter-rotating cylinders of air that trail behind the wingtips of an airplane whenever it generates lift. These vortices, as they're called, can induce rolling or structural damage to an aircraft that inadvertently encounter them, usually on takeoff or landing. What most pilots don't know is that helicopters can generate vortex circulation also. These vortices trail behind the helicopter in a manner similar to wingtip vortices generated by airplanes. The vortex strength is greatest when the aircraft is heavy, clean, and slow. So watch for wake turbulence even around helicopters. Now we come to one of the most important aerodynamic factors affecting rotorcraft flight, dissymmetry of lift. In zero airspeed conditions, like hovering in a calm wind, the airflow passing through the rotor system is equal across the entire rotor disc. As the helicopter moves through the air, however, the airflow going through the advancing half of the rotor disc is relatively greater than the airflow going through the retreating half. Let's use this example to illustrate. Assume the blade tip is going 400 miles per hour and the helicopter itself is flying forward at 100 miles per hour. Since both the helicopter and the advancing blade are advancing in the same direction, the total speed of the advancing blade is 500 miles per hour. Blade tip speed plus aircraft speed equals 500 miles per hour. The retreating blade is also moving at 400 miles per hour, but it's retreating or moving away from the direction the helicopter is traveling. So the total speed of the retreating blade is only 300 miles per hour. Blade tip speed minus aircraft speed equals 300 miles per hour. There's a relative difference in speed of 200 miles per hour between the advancing half versus the retreating half of the rotor disc. Even though the rotor is turning at the same speed on both sides, the advancing blade benefits from the extra airflow gained from moving in the same direction as the aircraft, while the retreating blade loses an equal amount. Thus, a dissymmetry or unequal lift across the rotor disc occurs in horizontal flight. The difference in relative wind speed means the advancing blade produces more lift than the retreating blade. Dissymmetry of lift is sort of like riding an escalator. If you just stand there, you go the same speed whether riding up or down. But if you walk up the escalator or advance while it's moving up, your average speed is pretty fast. By the same token though, if you try to walk down or retreat on an escalator that's moving up, your average speed is pretty slow. All things being equal, dissymmetry of lift would cause the helicopter to roll in the direction of the retreating or left side of the rotor disc when in forward motion. This would make for extremely awkward flying. Fortunately, there's an elegant yet simple cure for this problem. It's called flapping. Flapping alleviates dissymmetry of lift. Rotorcraft designers designed the rotor system so that the blades can move up and down freely. In a fully articulated rotor system, a horizontal flapping hinge allows each blade to move up and down independently. In a semi-rigid system, the blades move up and down as a unit about the rotor mast, much like a teeter-totter. This is why two-bladed systems are sometimes called teetering rotor systems. Rigid rotor systems achieve the same effect by way of blade bending. Here's how flapping works. The greater relative lift generated on the advancing side of the rotor disc causes the advancing blade to flap up. This upward movement, with respect to the relative wind, reduces the angle of attack of the blade, thus decreasing lift. Just the opposite occurs with the retreating blade. The reduced lift on the retreating side causes the blade to flap down, increasing its angle of attack, thus generating increased lift. If this sounds complicated, it's really not. Let's summarize this entire process in a table. Dissymmetry of lift causes an increase in angle of attack on the advancing side, which causes an increase in lift, and a decrease in angle of attack on the retreating side, which causes a decrease in lift. Flapping up on the advancing side decreases lift, while flapping down on the retreating side increases lift. Bottom line, flapping cancels out the dissymmetry of lift. This automatically equalizes lift across the entire rotor disc. There are practical limits to how far the rotor blades can flap. At high forward air speeds, dissymmetry of lift becomes so great that flapping can't alleviate the imbalance any longer. As you saw a moment ago, there can be a difference of 200 miles per hour in speed between the advancing and retreating blades because of dissymmetry of lift. Suppose you increase your forward speed to 150 miles per hour. The advancing blade is now going 550 miles per hour, and the retreating blade is going 250 miles an hour. Now a difference of 300 miles per hour. As you increase your forward air speed, dissymmetry of lift grows greater and greater very quickly. You eventually reach a point where insufficient lift on the retreating side becomes a real problem, and the only way the retreating blade can produce more lift is to increase its angle of attack. Eventually, the relatively slow retreating blade exceeds its critical angle of attack and stalls. The advancing blade continues to produce lift, so we end up with a helicopter that's stalled only on the retreating side. That's why this flight condition is called retreating blade stall. Engineers calculate the forward airspeed at which retreating blade stall is likely to occur for each model of helicopter. This becomes the rotorcraft's never exceed speed, or VNE. It's interesting to note that VNE in rotorcraft and VNE in airplanes are calculated differently. VNE in airplanes is determined by structural limitations, but in rotorcraft it's retreating blade stall. A number of factors will increase the likelihood that retreating blade stall will occur. These include high gross weight, high true altitude or high density altitude, turbulent air, low RPM, steep turns, and abrupt maneuvers. You should reduce VNE under these conditions in order to avoid retreating blade stall. The major indications of retreating blade stall situation are a low frequency vibration, the nose pitches up, and there's a tendency for the helicopter to roll. Here's a brain teaser for you. If the rotor disc is stalling on the left, why is it pitching up instead of to the left side? Remember gyroscopic precession? The stall won't become noticeable until it rotates another quarter turn towards the rear of the helicopter. Similarly, the high lift generated on the advancing right side will move to the front, hence the nose pitch up. You correct for retreating blade stall by dealing with the causes. The pilot should react by reducing the collective pitch to lower the angle of attack, increasing the rotor RPM within allowable limits to increase lift on the retreating side, and reduce forward airspeed by applying aft cyclic to reduce the dissymmetry of lift. Also, keep maneuvering to a minimum. There's another phenomenon associated with flapping. As you can see in this graphic, When a blade flaps either up or down, its center of mass moves somewhat closer to the axis of rotation. When this happens, a force called Coriolis effect causes the blade to accelerate. Let's use the example of a figure skater to show this. While performing a spin with her arms extended, she tends to spin rather slowly. But when she draws them in towards her rotating body, she begins to spin faster. In the same way, when a rotor blade flaps up or down from true horizontal, its center of mass moves somewhat closer to the axis of rotation, and the blade accelerates. Let's illustrate this with a graphical example. The rotor blades are at true horizontal when they're at the 12 o'clock and the 6 o'clock positions, and their center of mass is furthest from the axis of rotation. As the blades rotate, they flap, causing the center of mass to move closer to the axis of rotation. Notice that as the blades rotate, they accelerate slightly. In this example, from 400 miles per hour to 405 miles per hour. Then as the blades continue rotating, they again flap towards true horizontal. The center of mass moves further away from the axis of rotation, and again the blades decelerate. We describe this back and forth blade motion as leading and lagging around the axis of rotation. It's also called dragging or hunting. A variety of hinges, dampers, or even the blade structure itself absorbs these acceleration-deceleration actions. In a fully articulated rotor system, a vertical drag hinge allows the rotor blades to lead and lag to compensate for Coriolis effect. Notice in this two-bladed system, there are no drag hinges. In a semi-rigid system, the blades are generally underslung with respect to the rotor hub, and the change in the distance of the center of mass from the axis of rotation is small. The lead-lag motion is absorbed by the blades bending. Lead lag is usually not significant in rigid systems and is also absorbed by blade flexing and bending. As we discussed earlier, flapping compensates for dissymmetry of lift. And as we just saw, dragging permits the lead lag associated with Coriolis force. Finally, all rotor systems must also be able to feather. Feathering is the span-wise rotation or twisting of the rotor blade. This twisting changes the pitch angle of the blade. Remember that the blade pitch angle is the angle between the blade chord line, running from the leading edge to the trailing edge, and the rotor plane of rotation. It's necessary to change or feather the blade pitch angle in order to increase or decrease the angle of attack, which in turn increases or decreases the lift. Remember that the collective increases or decreases pitch angle on all the blades simultaneously or collectively, while the cyclic changes pitch of each blade individually as it passes or cycles through the same position in the plane of rotation. Well, that pretty much covers it for helicopter aerodynamics. We can get into lots more detail, but I think you've got the big picture. As you can see, the helicopter pilot has to be aware of a variety of aerodynamics that the average airplane pilot never even needs to think about. We've arrived now at the section on performance. This includes factors that reduce performance, hover ceilings, rate of climb, the RPM-MAP relationship, and the height versus velocity chart. Let's get started. Helicopters need almost every ounce of power available to fly. There's very little to spare. Therefore, you need to be aware of factors that can reduce the helicopter's performance. Here's an easy way to remember them, the 4 H's. High, meaning high altitude, hot, or high outside temperature, humid, high humidity, and heavy, or high gross weight. Notice that the first three, high, hot, and humid, all contribute to high density altitude. Anything that increases density altitude, such as hot temperatures or high humidity, will reduce both rotor and engine efficiency. The rotor can't generate as much lift in the thinner air found at high density altitudes. and the engine can't produce as much power in the decreased atmospheric pressure. High gross weight degrades performance by increasing coning, which decreases the lifting area. And if you're already close to maximum gross weight, banking, for example, will increase the load factor beyond that limit and make the engine work harder to lift more weight. A calm wind condition also decreases performance. Why? Well, in order for the helicopter to take advantage of effective translational lift, it needs to reach an airspeed of about 15 miles per hour. With a moderate wind, you'll only need a minimal amount of ground speed before effective translational lift gives you that desirable boost. So, to summarize, the most unfavorable conditions for rotorcraft performance are high density altitude, high gross weight, and calm wind. And remember, rotorcraft performance suffers even more than an airplane under these conditions. In order to operate safely in marginal conditions, the smart helicopter pilot knows when and how to calculate various rotorcraft limitations. We just talked about how air temperature and gross weight affect performance. How do we calculate their effect on hover ceiling, for example? Using just a little bit of available information and the appropriate chart in our rotorcraft flight manual, we can figure it out. Let me show you how. Going to the in-ground effect chart, we locate 1,225 pounds on the bottom. Moving upwards from 1,225 pounds, we intercept the temperature at 25 degrees centigrade. Note the temperature conversion chart up above. 77 degrees Fahrenheit is equal to 25 degrees centigrade. From this intersection, proceed horizontally to the left and read the calculated in-ground effect hover ceiling. It's equal to 6,750 feet. That's all there is to it. Just be sure to use the correct chart, either the in-ground effect or out-of-ground effect charts, and be careful when locating the weight and converting the temperature. There's another type of performance limitation that's greatly affected by poor conditions, the helicopter's rate of climb. Let's do an example to show how to calculate rate of climb. Go to the rate of climb chart and find 4,100 feet on the vertical axis. Draw a line to the right until you intercept 90 degrees. Notice that there isn't actually a 90-degree line, so you'll need to estimate or draw a 90-degree line right in between the lines for 80 and 100 degrees. Finally, draw a line down to the rate of climb axis, and you'll see that it intersects it at 250 feet per minute. It's recommended that you accelerate slowly into forward flight during takeoff in these conditions. Let me advise you again, be careful. Most people make mistakes from misreading the charts, not from doing the actual calculations. Now let's examine the relationship between RPM and manifold pressure. You may find yourself in a situation where your RPM or manifold pressure is too high or too low. Perhaps the RPM is too low and the manifold pressure is too high. Or maybe the RPM is too high and the manifold pressure is too low. It can get confusing. There's no shortcut to remembering the appropriate action to take. It depends on the combination of RPM and manifold pressure, but it's not all that complicated. Take a look at this chart. When the RPM is low and the manifold pressure is low, you must increase the throttle to increase both the RPM and the manifold pressure. Just remember, when they're both low, increase throttle. When the RPM is high and the manifold pressure is high, decreasing the throttle will reduce both the RPM and the manifold pressure. Remember, when they're both high, decrease throttle. When the RPM is high and the manifold pressure is low, raising the collective pitch will increase the manifold pressure, which increases drag on the rotor, thereby decreasing RPM. Remember, low manifold pressure requires higher collective. And when the RPM is low and the manifold pressure is high, lowering the collective pitch will reduce manifold pressure, decrease induced drag on the rotor, and increase RPM. Just remember, high manifold pressure requires low collective. Notice how one control change can accomplish two goals. This illustrates the interrelationships between collective, throttle, power, and RPM. And remember to use smooth control inputs. Don't overreact. Finally, no discussion of helicopter performance would be complete without addressing the height versus velocity chart. Take a look at this chart. The height versus velocity chart describes unsafe altitude-airspeed combinations. Operations within the shaded regions are dangerous and should be avoided. The principal reason is that there would be insufficient airspeed to auto-rotate successfully in the event of an engine failure. To determine whether a particular airspeed-altitude combination should be avoided is a simple matter of finding where the two intersect on the chart. For example, here are three different combinations of airspeed and altitude. A, 30 miles per hour, 200 feet above the ground. B, 50 miles per hour, 300 feet above the ground. Or C, 60 miles per hour, 20 feet above the ground. Which of these should be avoided? Starting with A, we draw a line up from 30 miles per hour and then draw a line over from 200 feet. Does this point lie within a shaded region? No. So operating at 30 miles per hour at 200 feet AGL is safe. Do the same for B. Draw a line up from 50 miles per hour and a line over from 300 feet. Does this point lie within a shaded region? No again. How about C? Drawing a line up from 60 miles per hour and a line over from 20 feet, we see that the intersection of the two lines falls within the lower shaded region. Operating 60 miles per hour at 20 feet AGL would be considered dangerous. Response C would be the airspeed-altitude combination to avoid. An example of a maneuver that could get you into trouble with the height versus velocity chart would be making a downwind turn close to the ground immediately after takeoff. Why? Well, you know that when you turn downwind, you're going with the wind instead of into it. This causes the airspeed to decrease. Making a turn under these conditions will put you into a dangerous airspeed-altitude region of the height-velocity chart. Therefore, it's not a good practice because it increases the hazard involved should an emergency landing become necessary.